Okay, thank you very much for the introduction. It's my great honor to give a tutorials on the topological aspect of spin textures in 3 dimensions. And I have a subtitle here from Skyrmion to hopfion because I want to give an introduction of the Skyrmion to show where we are. It's also an introduction remark for 2 exciting talks by Shinichiro and Vincent. And the main goal of this talk is to talk about 3 dimensions, especially hopfions, and this will be an introduction remark to the talk by Philip in the next session. So the topology of magnetic system can be traced back to the topology of magnetic ring. So here, if we allow all the spins to lie in the plane, then there were 2 topologically distinct structures. One is the spin polarized state, and the other is the vortex state, in which the spins are fanning out. So if we want to transfer from the vortex to the spin polarized state, you keep this spin unchanged, and you like to rotate this spin in the counterclockwise direction by a small angle. And this angle gradually increases, so on and so forth. Eventually, you see that the spin to the left of this rotated by an angle of 2 pi, while the one to the right rotated by a very small angle. And this rotation angle is not continuous across the North Pole. So there's no continuous deformation between these 2 textures. So this explains their topological difference. And this can be generalized into 3 dimensions. Again, 2 configurations, spin polarized, and the other is the fan-out hedgehog state. If you see this the magnetic moment of the hedgehog at the magnetic field originating from a monopole sitting at the center, and there's no monopole involved for the spin polarized state due to the Gauss law. So the presence and the absence of magnetic monopole somehow indicates their topological difference. And this hedgehog is actually closely related to the Skyrmion by the so-called stereographic projection. What you do is to place this hedgehog on top of 2D plane. Then you draw a couple of lines connecting to the North Pole, and this line would intersect at the unit sphere at this point, for example, and then you give this spin to the spin at the 2D plane. Just project this hedgehog configuration onto the 2D plane. And what you get is this neo-type Skyrmion that has been realized in magnetic multi-layers. And if you rotate all the spin by the z-axis, about z-axis by an angle of 90 degrees, and you get another type of Skyrmion. So this is the block-type Skyrmion, realized mostly in bulk systems. So the lesson from this stereographic projection is this hedgehog, if we regard it as a singularity, because there's singularity at the center of the hedgehog. So this is regarded as defect. So it is S2 related to this sphere, S2 defect in 3 dimensions. And this will correspond to a Skyrmion, which is a spin texture in 2 dimensions. And you can generalize this correspondence by decreasing reducing the dimension by 1. And then there will be S1 defect in 2 dimensions, which will be the vortex. And this will relate to a texture in 1 dimension. And this is nothing but a domain wall. So there is a correspondence between these 2. And you can generalize it by elevating the dimension by 1. And what you get is a S3 defect in 4 dimensions. And this would correspond to a texture in 3 dimensions, which is the hopfion that I'm going to talk about. But let's postpone this because there is an intimate relation between the hopfion and the Skyrmions. So let's try to understand Skyrmion in more detail. So as a topological texture, there will be topological index. And topological index, again, we start from the vortex state. And the topological index of this one is just the number of spin rotation while you traverse the ring. And because this spin rotation will be always in unit of 2 pi, then you divide by 2 pi, you always get an integer value. And in calculus, you would, Yeah, in calculus, you were told that the total derivative can always be discarded. But in topology, you always need to keep it. So then we generalize into 3 dimensions. And the total derivative of the angle right now will be replaced by the total derivative of the solid angle. And the solid angle is always, 4 pi, you divide by 4 pi, you always get an integer value. But this solid angle, as you learned from 2-dimensional calculus, and this can be replaced by sine theta d phi, where theta is the polar angle and the phi is the azimuthal angle. And in skyrmions, this theta and phi depends on the position. Then you do a substitution of the integral variable. You eventually get this nice equation of the topological charge, where n is the direction of the spin point to point. And the definition of this topological charge, if we apply to a rotational symmetric configuration, and the things can be much simplified, because in this case, theta and phi, they are 2 independent variables, and you can integrate them over. And this part is total derivative, and this will be delta change of the cosine theta, and this d phi integrate over will be the change of phi while you traversing the peripheral of the texture. So let's take an example of this work by Stewart. They realized the anti-skyrmions in Heusler compound. So for each configuration, this is a box-type skyrmion. The change of cosine theta is a change of the z component of the magnetization between the center and the peripheral. For this one, the center is pointing down, peripheral is pointing up. So the change is 2 divided by 2, you'll get a 1 for block-type skyrmion. And that's the same for all these configurations. And then let's consider this one. The change of the azimuthal angle while traversing the peripheral. For this one, and you figured out it is always 2 pi. Divide by 2 pi, you get 1. And this is the same value for new-type skyrmion. So that tells us that no matter you change the sign of DM interaction, change the direction of DM interaction, you will probably get the same topological charge. And so this is a misunderstanding in the community. Sometimes we think, we change the sign of the DM interaction, we can change the topological charge, but this is another case. But for anti-skyrmion, this happens to be -1. So that's why the topological charge can be reversed. Another way to reverse the topological charge is you flip your external magnetic field that's stabilizing the configuration. And then you change this part. And also because the topological charge involves 3 spins and it breaks time reversal symmetry, in order to reverse it, it's naturally to flip the external magnetic field. And this skyrmion was first discovered in manganese silicide. And this is the crystal structure of manganese silicide. Red bars for silicon and blue bars for manganese. If you perform the inversion with respect to center, you will see that blue and bars exchange. And no matter how you translate the whole lattice, there's no way that these 2 configurations can be coincide with each other. And the consequence of this one, we already know, is the DM interactions. And for manganese silicide, this DM interaction is pointing from one spin to the other. Okay, so this is the direction of DM interaction. But this spin is not the microscopic spin sitting on each manganese. It's an effective spin from each unit cell. Because from the so-called molecular rule, you will never, ever get a DM vector direction in that way. And the consequence of this one is there will be a small angle in between 2 neighboring spins, and this angle is determined by the ratio of DM interaction and Heisenberg exchange. And then if you have an array of spins, you'll get a helical configuration. And this is the propagation direction of the helix. Then you apply magnetic field, you'll get a conical phase in which the spin is rotating on the cone surface. And this is the phase diagram of manganese silicide. Low temperature from, with the increasing magnetic field, the system undergoes successive transition from helix to conical to spin polarized state. And this is the skyrmion phase. Okay. So this skyrmion phase is at finite temperature. So that shows the thermal fluctuation is very important in bulk systems to stabilize the skyrmion. So there is another sign of this phase diagram is, you see here, it looks like a discontinuity point. Okay. The real phase boundary should be something like here all the way down. But why it's vertical here? Okay, because this part of phase is suppressed by the thermal fluctuation. And this transition from the skyrmion to the paramagnetic state is supposed to be a second order phase transition due to the symmetry perspective. But due to the large thermal fluctuation, the second order phase transition is suppressed to be first order phase transition. And another ingredient to stabilize the skyrmion is, of course, the DM interaction. And DM interaction can be understood by looking to the configuration. Here, the center spin is, if you see the spin configuration along that direction, here spin pointing into the plane, here in that way to the left, here out of plane, then to the right, and this is nothing but a spin helix. And then along that direction, another spin helix, and another spin helix. So skyrmion lattice is a superposition of 3 equilateral spin helices. And skyrmion has been realized in a list of materials here. And also, these are B20 compounds sharing same lattice structure and manganese silicide. But there are also other lattice structures like beta manganese structure. They belong to the O point group. And this copper zinc manganese is the room temperature skyrmion. And we also observed another one in this complicated compound. But there is not much work following this one because the lesson we learned is, as a series to make some experimental prediction, correctness is important, but price is also important. Rhodium is very expensive. So this is the main problem of this material. And also, skyrmion has been realized in a series of RKKY alternate magnets. And Chinchilla will talk about this one, especially this gadolinium ruthenium silicon. So this material has has inversion symmetry. And DM interaction is not there. And skyrmion there is stabilized by 4 spin interactions. Actually, 4 spin interactions is very important even in the conventional manganese silicide compound. Then Vincent will talk about interfacial skyrmions, I assume. So this is a groundbreaking work on the interfacial skyrmions. The idea is the inversion symmetry is broken by the asymmetric stacking of these magnetic thin films. So there is a mirror symmetry breaking, and the mirror symmetry relate to inversion symmetry by a 2-fold rotation symmetry. Then this is a series of interfacial skyrmions realized in all kinds of different materials. Then I would like to briefly talk about the skyrmion dynamics. Skyrmion, the magnetizations follows this ALG equation. And this is the Lamarck precession, adiabatic spin transfer torque. And phenomenologically, one can add another term, the non-adiabatic spin transfer torque, which is perpendicular to the spin transfer torque term. And eventually, there is the Gilbert damping. So we want to solve this equation. And there are several ways. One is do the numerical simulation, microscopic, micromagnetic simulations you can get a lot of details of the dynamics, including the magnon excitations. But what we are interested in is the collective motion of the skyrmion. And in this way, we'll introduce the displacement of the skyrmion R. And the magnetization dynamics as function of position and time will be written as the collective motion of the stable ground state skyrmion by R. And all time dependence goes to this displacement. And then there is a term like this one. We can write in terms of this. And xy is just xy component of the position. Next thing we do is we multiply by this term on both hand side and integrate over a skyrmion configuration. Then this partial m, partial x is the same as partial m, partial x. This term doesn't contribute. And only this term contribute. And this is m not partial x m, partial y m. This is exactly the integrand of the topological charge. You integrate over, you get this one, and Q is the topological charge of the skyrmion. So you can do the same manipulation of all other terms. Eventually, you get this nice equation motion for the skyrmion. And this V is the velocity. U is proportional to the current density, the density of current you applied. And the G is given by this. D is just a boring number on the other one. And it describes some microscopic distribution of the magnetization. Now we solve this equation. To solve this equation, first we notice alpha and beta. They're very small. They related to dissipation. Alpha is the Gilbert damping. Beta is the non-diabatic spin transfer torque. They're very small. Let's forget about that. And this equation, we can solve it in 1 second. That is V equals to U. Okay. Velocity of skyrmion is the same as is proportional to the current you applied. Then you include this as a perturbation. Then you get a transverse velocity. And this is the skyrmion Hall effect. And this has been examined in a series of works. This is our recent collaboration with the experimental group in China. And we work on copper, zinc, manganese. And you see the trajectory of the skyrmion. Current is applied along x direction. And skyrmion is moving that direction. If you take a snapshot, you can focus on these two columns. Current is the same. Topological charge is flipped because the magnetic field, external magnetic field is flipped. And this skyrmion is moving down. This skyrmion is moving up. They have the opposite topological, opposite skyrmion Hall effect. And this is nicely consistent with this equation. I'll talk about velocity later. Yeah. Then a nice thing is, I mean, in general for devices, we don't like a skyrmion Hall effect. We want the trajectory of skyrmion exactly parallel with the external current. And what one can do is to make a lateral dimension, dimension restriction. And in this case, we can phenomenologically include a force attributed to the constriction and allow this force to cancel with this one because they're both in the transverse direction. Then we have another equation that is very easy to solve. This equation will get a solution that the velocity of skyrmion is beta over alpha times u. Both beta and alpha are very small, but their ratio is not necessarily small. And for iron germanium, later I will show that the velocity of the slope of the velocity current curve will be largest in iron germanium. Yeah, this is very, very surprising, actually. So this is the experimental observation. So again, the same group, -2 from High Magnetic Field Laboratory in China, they fabricated an iron germanium nano ribbon, a nano wire. This wire is only 100 nanometer thick, wide, but 10 micrometer long. In this case, skyrmion is confined. And the velocity of skyrmion can approach to about 100 meters per second. And this is a relatively straightforward way, but there's actually another way to realize what is what? Velocity peak here. This is, there is a little bit of variation of the duration of the pulse you applied. Oh, here. Yeah. So we still try to understand this one, whether this is, this saturation, this part, probably it is related to the thermal heating. Yeah, you apply a large current. Yeah. So yeah, this is still something that we try to understand in nano ribbon. Duration of the pulse. Yeah. Another way is to put the skyrmion in between helical lanes. And so this is the so-called interstitial skyrmion. And we design a notch here. Then at the ground state, there is helix lanes. And once a current is sent through the notch, you see there is a skyrmion here. And this helical lane provides a highway, and skyrmion can only move along the lane. Then we can talk about velocity. For this case, the velocity as function of current is almost a straight line. And the slope is 8.3 10 to minus 10 up to some SI unit. But in 2 dimensions, free motion of the skyrmion, and it's also a straight line, the slope is only about 1.0. So compared to this equation, it shows that iron germanium has beta over alpha ratio about 8.3. So that is very surprising. So we try to introduce some phenomenological model eventually. This magnetization of this dynamics of magnetization. This is dynamics of the spin, conduction electron. And one can solve for the torque applied to the magnetization. Eventually, we'll get this conclusion. Okay, so this is the beta. And alpha, the Gilbert damping, is introduced by another work by Connell. And this tau is the spin relaxation time. But in reality, this tau could be very complicated. But we assume that these 2 relaxation time the same. Then, as a result, beta over alpha would be tau independent. So this will be an intrinsic property of the material. And we can perform some DFT calculations, and we show that iron germanium literally have beta over alpha about 8. But for all conventional ferromagnets, this beta over alpha is only about 1. Then we move on to 3 dimensions. In 3 dimensions, there are a lot of interesting textures, like skyrmion strings. That is the case in most bulk materials. And Shinichiro will talk about this, I guess. And Vincent will talk about the skyrmion cocoons. While preparing this slide, I feel that this is really a challenge to my vocabulary. And there's also chirobubbles. And this skyrmion is terminated at a block point, a singularity. But if the top of the skyrmion is also terminated by another block point. And this will give you the cocoon, if I understand it correctly. And there are also the case that there were two skyrmion tube going down and terminated at a single skyrmion tube. And in between, a block point or singularity is doomed. And there are also some, we're involved in some three-dimensional textures like a iron germanium tetrahedron. Iron tetrahedron, this is the electron holography measurement, and electron beam is sent in these three different directions. And this is our microscopic, micromagnetic simulation. And this basically recovers the configuration experimental observed. So the conclusion is in iron germanium tetrahedron, 100 nanometer sized, without external magnetic field, there will be a skyrmion tube starting from the center of the edge and going up, terminated at the center of the opposite edge. And the reason for this is there is some so-called geometric chiral frustration. Consider a chiral magnet 2D plane. Because there is no spin outside the plane. At the edge, the spin is basically rotating. But then, if you fold this 2D sheet, and this is the folding edge. So this is one plane, and the spin will be rotating in this direction. And in this plane, the spin will be rotating in this direction. Then eventually, at the folding edge, the spin doesn't know which direction to point to. And the result is a compromise. So half spin pointing in one direction, half spin pointing in the opposite direction. Then the problem is what it is at the center. And the result is spin will stick out of plane. So now we back to the tetrahedron. There is a plane here, and there is another plane here, and this is the folding edge. At this folding edge, then at the center, there will be a vortex state like this, and spin is sticking out of plane, as you see here. And this, the red edge is another folding edge of this plane and this plane. And the spin is again sticking out of plane. Then at the center, this spin is basically pointing down. And this provides at the backbone of the skyrmion tube. And also, we have realized another interesting configuration, the skyrmionium. And skyrmionium has been introduced in earlier work by Bogdanov. And this is skyrmion from center to peripheral. The spin rotates by an angle of pi. But for skyrmionium, from center to peripheral, the spin rotated by an angle of 2 pi. And this rotation, if you use the color plot to stand for the in-plane spin directions, and the skyrmion will be replaced by, will be visualized by this disk, and the skyrmionium will be a disk wrapped by a circular helical lane. And this rotation angle can be generalized, and then there will be a series of concentric helical lanes. Okay, so this is the target skyrmion. And target skyrmion, we predict that it can be realized in iron germanium nanodisk with a thickness that is comparable to the skyrmion size. And this is the three-dimensional configuration. And in this, because this configuration is stabilized without external magnetic field. So there are two configurations sharing same energy, and they are just a time reversal partner to each other. All spins are flipped. Here, one configuration spin down, then spin up, spin down, and another one spin up, spin down, spin up. They just share the same energy, and this has been experimentally realized. And there's actually another way to realize the skyrmionium is through the skyrmion bundle. If again we see this helical stripe as a bag, okay, containing a skyrmion in the center, then this bag could contain more skyrmions, just like this. And we did some micromagnetic simulation. And the way to realize the skyrmion bundle is to take advantage of non-equilibrium spin configuration. So what does that mean? So first, you cool down, turn off a field that was originally applied in the negative direction. Say spin pointing down, field pointing down. Okay? Then you gradually turn that off. And once you turn it off, at zero field, you get helical lengths. And then there is some skyrmion still remains. And this skyrmion had a center spin pointing opposite to the external field. So it will be pointing up, pointing out of plane. Then you gradually increase the field in the positive direction. And these skyrmions with the center spin pointing up will be unstable. Most of the skyrmions are gone. But there are some skyrmion remains, and they are stabilized because they happen to be wrapped up by these remaining helical lengths. So this is the skyrmion bundle. But I have to confess that the number of skyrmions in the bundle is not under control. But no matter how many, I should have, sorry. Yeah, let's talk about this first. And no matter what the number of skyrmions in bundle, you gradually increase the field, and the system would undergo successive cascading transition, and the skyrmion in the bundle will be annihilated one by one. And eventually, you only have one skyrmion remaining. And this is skyrmionium. And if you further increase the field, the skyrmionium will collapse to a conventional skyrmion. And this skyrmion will stay for a long time. But there is a three-dimensional structure, okay, for this skyrmion bundle. This is our simulation. At the center, it is what as expected, skyrmions wrapped by a bag. But at surface, you see this skyrmion bag is melted into a chiral vortex. And so this is the equal MZ contour of this skyrmion, this chiral vortex. And if you're traversing the peripheral of this vortex, and the azimuthal angle will rotate by 5 times 2 pi. And that's why the topological charge here, it is 5. Okay. And at the center, you just count the number of skyrmions. Each one gives you 1. And then there is a helical lane outside. And this helical lane will give you a topological charge of -1. Okay. So that's why the topological charge is 5. And this is this. And this is the simulation. So at different layers, you will see that at the center is skyrmion bag. And if you move further to the bottom surface, this skyrmion bag will be melted. And eventually, you get another chiral vortex.
What do you mean that this MZ is equal to 0.7?
MZ, yeah, so here it's not. So this is the contour for MZ equal to 0.7. Yeah, you can plot the contour for other MZ values, and they were basically the same. And there's also dynamics of skyrmion bundles. You apply a current. Yeah, okay. You apply current along x direction, you see that this skyrmion bundle will move. But it's also accompanied by a skyrmion Hall effect. So this completes my discussion of the skyrmion. Then let's talk about hopfions. So we try to realize the topological spin textures in 3D. And hopfion is the only topological texture that I know of. Again, just to remind you that this hedgehog and the vortex, they are defects because there is a singularity at the center. And the skyrmion is a texture. By texture, I mean the configuration without singularity. And hopfion will be the one. And how to construct a hopfion? Again, we borrow our knowledge of the skyrmion, the stereographic projection. Right now, we do it quantitatively. For any point on the 2D plane with a coordinate x, y with respect to the origin, you draw a line, connect to the North Pole, and then this intersect at the unit sphere at P, and P has the coordinate of n1, n2, n3 from the center of the sphere. And this n1, n2, n3 is is given by this equation. Now, as I said, in order to construct hopfion, we need to elevate the dimension by 1. So this is a map from one point in 2 dimensions to a one point in S2. Now we can construct a stereographic projection from one point in 3 dimensions to a point in the unit sphere in 4 dimensions. This is the same, this is the same, this is the same. Then you can easily make up at the third term. You replace x, y by z, and that's it. And this is normalized. Then we want to construct a map from S3 to S2 because the spin lies in a unit sphere in 3 dimensions. How to do that? So the way to do that is actually given in the textbook of quantum mechanics. So from these 4 numbers, you can construct a spinon like this. And this spinon is automatically normalized. Then you calculate its expectation with respect to 3 Pauli matrices. And you get this n. And this n is exactly a hopfion configuration. So by this way, you can construct a hopfion configuration explicitly given by this equation. And then let's talk about topological charge. Topological charge of skyrmion is n dot partial x n cross partial y n. And can also be equivalently written in terms of these indices. And this epsilon is total antisymmetric tensor. Ni partial mu, nj partial nu, nk. And then what is the topological index of a hopfion? You just make up a new term, partial rho psi L, and total antisymmetrize all these components and total antisymmetrize all the derivatives. So, and this is, we know that it's the integral of a emergent magnetic field. And this will be an integral of B dot A. Okay. B is the 3-dimensional emergent magnetic field. A is any vector potential as long as its curve will give you this field. A little bit of history of the hopfion. This hopfion was originally introduced by Heinz Hopf. And his contribution is to realize this map from S3 to S2, okay, as I introduced. But then there was another interesting work by Adam. He generalized the Hopf map. And there are only 3 Hopf maps that can exist in nature, no others. One is S3 to S2, we already introduced. There's another one, S7 to S4. S7 to S4 has the physical meaning of the Dirac theory, relativistic quantum mechanics. Because in Dirac theory, the spinon is 4-component, 4-component complex spinon. So this is in S7. This is in this S4. Yeah. And in Dirac theory, we have altogether 8 Clifford matrices. And here there are 3 Pauli matrices. So that is related to this one. And then there's another one, S16 to S8. And we don't know the physics. Probably there is another physics beyond the relativistic quantum mechanics that is related to this Hopf map. And this Hopfion was also discussed intensely in the so-called Skyrm-Faddeev model. And Faddeev introduced this nice equation, satisfied all symmetries, renormalizations that you can imagine. And a Hopfion configuration will be a matter-stable state of this Hamiltonian. And the energy of each Hopfion will be lower bounded by its topological index. And my favorite example of Hopfion is this one by Lanada. And what they say is this ball lightning is an electromagnetic Hopfion. So this is really cool. And this is a recording of ball lightning in 1907 in Basel. We are still debating whether this is true or not. So probably if in the future I find that myself cannot survive in magnetic community, I'll do the ball lightning. Now let's talk about the topological index of Hopfion. B dot A. Okay, what is the meaning of this one? So it has actually a geometrical meaning of the linking number. A spin configuration in 3D is actually mathematically regarded as a map from R3 to S2, as I introduced. Right? But if you're given a spin direction, and you can ask, what are the positions of spin that give rise to that direction? So this is kind of inverse map from S2 to R3. But this is many to one map, and this one will be one to many map. Right, so this is called a preimage. For example, if we are trying to find locations of spin pointing in that direction in a Hopfion configuration, it will form a closed loop. It must form a closed loop because in Hopfion, our assumption is there is no singularity. Okay, it's continuous, so it must be a closed loop. And for that direction, you can find the preimage, you find another closed loop. And these two loops will be linked. And no matter what the choice of S2 and this two closed loop will always be linked by the same linking number. And this linking number is determined by this one. So for example, we can find a bundle of preimages with their spin direction in the equator, of this unit sphere. And you will see that this closed loop is expanding, and eventually it will form a torus. On the torus plane, all the spins has vanishing MZ component. And this is a distribution of the spins in a Hopfion configuration. And there's actually a close relation with of the Skyrmion and the Hopfion. what you do is you can take a series cross sections, and you will get a series of skyrmions. And this skyrmion has their helicities changing from the neotype skyrmion to block, and even in between the skyrmion and anti-skyrmion. So this is a key feature. So this is the hopfion. If we take a cross section of this large a large circle, an XY plane, and you will get a configuration like this. Color stands for the in-plane spin directions. So what is this configuration? This is actually a skyrmion. Center white, spin say into the plane. Here black, spin out of plane, and then spin back into the plane. So this is exactly a skyrmion. So if we take a cross section of this YZ plane, right, this plane, and this is spin configuration. Here you see it's red, blue, green, and here red, green, blue. They're rotating in opposite direction. So here is a skyrmion, and this is the anti-skyrmion. So this I will regard as a key feature of hopfions. If you happen to have a hopfion, you should take the take whatever Lorentz TM or electron holography in these two directions, and you'll see different configurations. And the correspondence between a skyrmion and a hopfion can be visualized in this animation. What you need to do is just to twist the skyrmion tube by angle 2 pi, then connect two ends, and you get a hopfion. And this skyrmion hopfion has been realized, has been predicted in our work to be realized in a nanodisk of chiral magnets sandwiched in between two spin porous layers, and this has been realized very nicely by Peter's experiment. Of course, the approach is a little bit different. Here it's multi-layers, and by changing the stacking sequence, and you can have the chiral magnet in center and the spin porous at the periphery. But the physics is quite similar. This hopfions has been also realized in iron germanium. In this work, you'll see that they take the Lorentz TM along Z direction and also cant it. And then you will see that in the Z direction, it is the target skyrmion, the skyrmionium. But once you cant it, there are two skyrmion will converge, and they have different topological charge. So this is regarded as a strong evidence of the hopfions. And recently, there's a nice work that Philip will probably introduce, and this is skyrmion, these hopfions with the skyrmion strings at the center. And there's also another realization of hopfions here in a cylinder of iron germanium. Once there's a trench here, this is side view, you just dig it out and then apply current in the Z direction, and a hopfion can be generated dynamically. And this hopfions also has been predicted to exist in frustrated magnets with competing interactions. So I don't think I have time to talk about the dynamics of the hopfions. Basically, you apply current, and this hopfion will also move, but its torus plane will rotate. So that can be modeled in terms of yeah. So I'll just use 30 seconds to talk about the challenges of hopfion. it's very important to realize the hopfion in bulk materials. And also, it's also very important to realize the hopfion lattice. So the skyrmion, from my understanding, is so interesting because there is a skyrmion lattice that can be decomposed into 3 equilateral spin helices, as I mentioned. But hopfions, whether it can be constructed in terms of multi-Q state, this is the question. And how to image a hopfion, especially how to image these 3-dimensional magnetic orders. I'm seeing that there is a lot of developments. Maybe Claire will talk about this in terms of X-ray. And also, there's transport signatures. Skyrmion is interesting because there is a topological effect that is related to the topological charge. And a nice question one can ask is whether the Hopf index reveals itself in any transport signatures. And that hasn't been discovered yet. So with this, I'll skip the conclusions. And this is a list of collaborators, and the work has been supported by a US Department of Energy. With this, I'd like to thank you for your attention.